This video, we're going to prove the following two facts. Assuming that a and b are integers, but they're not divisible by their prime p. Then we need to show if a is congruent to, if a to the p is congruent to b to the p mod p, then in fact a and b are congruent mod p. The second fact, it starts off the same. If a to the p and b to the p are congruent modulo p, then a to the p is still congruent to b to the p, but with a different mod p squared. If you like seeing mathematical proofs like this, subscribe to my channel, as this is all we do. Okay. Now, note that p does not divide a and p does not divide b. Justification, it was given. Okay, so now by Fermat's-Little's theorem, that implies that a to the p is congruent to a mod p, and b to the p is also congruent, is congruent to b modulo p. Okay. Now, this implies the following. This implies that a to the p minus b to the p is congruent to a minus b. I subtracted these two congruences, mod p. Okay. Now, we are told this. We are given that. Now, a to the p is congruent to b to the p, this mod p. This implies that p divides a to the p minus b to the p. Well, that implies that a to the p minus b to the p is congruent to 0 mod p. So this is 0 mod p. Okay, so let's formally state it below. That implies 0 is congruent to a minus b mod p, which implies, actually, if and only if, to remind you, that a minus b is congruent to 0 mod p, adding b to both sides. I could have done that from here. Adding b to both sides, we get that a is congruent to b modulo p. And when it comes to part 1, that's exactly what we wanted to establish, that a and b are congruent modulo p. So let's put an a up here. Now for b, we're still given that a to the p is congruent to b to the p modulo p. Okay, this is what we are given, and we want to show that a to the p is congruent to b to the p mod q. Well, from part A, this implies that a is congruent to b mod p. That's exactly what part A said. Okay. Now, that implies that A is B plus a multiple of P. Now, this should say P squared. Somehow, I want to get that A to the P minus B to the P is a multiple of P squared. Well, this implies raising both sides to the P power. It implies this statement. But from the binomial theorem, we're going to have B to the P plus P times B to the P minus 1 times MP plus some binomial coefficient times B to the P minus 2 MP squared. Notice here we have our P times a P. Here we have P squared. And this continues all the way up to MP to the P. Now P is prime. That means it's at least 2. So once again, we have at least P squared. Well, this is equal to B squared plus, I can factor out a P squared plus everything else. But I can factor out a P squared. Well, this is congruent to B squared modulo P. This is 0 because P is 0. 0 squared is 0. 0 times some other number like Q is 0. So what I made one major mistake. That's not B squared. That is B to the P. B to the P, excuse me. So what we have is that A to the P. This implies that A to the P, which equals this, which equals that, which equals that, which is congruent to B to the P mod P squared. Mod P squared. Mod P squared. P squared is 0 now. I said P was 0, but when it comes to mod P squared, which is what we want, it's 0. And B to the P plus 0 is just B to the P. And this is what we wanted to show, and I did. If you like mathematical proofs, subscribe to my channel, click the like button, leave a comment. See you guys in the next video. Watch and learn.